Optimization uses everything that we've learned to maximize or minimize. Well, it can be anything. We're going to start off with a rectangle, but it could be cost. It could be the size. You can figure out the dimensions of something to maximize or minimize the cost or the volume or whatever you're doing. So let's start with the first one here. You have 70 meters of fencing. What is the maximum area you can enclose inside of a rectangle? So first thing I always do is draw a picture of a rectangle in this case. Label the sides. It doesn't matter what variable you use. It's your choice. I'm going to choose X and Y. Okay. What are we trying to maximize? The area. So what's the formula for area of a rectangle? Yeah, length times width, or in this case, X times Y. Okay. We need another formula. Okay. And we have another piece of information. We know that we have 70 meters of fencing. What does that 70 meters represent? The perimeter. What is the perimeter of a rectangle? All sides added together. So in this case, it would be 2x plus 2y. And we know that that has to equal 70. Okay? Everybody with me? Okay. We want to maximize the area. In order to maximize something or to find those dimensions, think of the area as a curve. I'll just draw it on here. You don't have to draw this. But the area is going to be like that. All right? If this is going to be area, and this is going to be, say, dimensions here. I want to maximize the area. Okay? So how do you find the maximum or the minimum in calculus? What do we do?
Derive and then define this.
Yeah, so it's where the derivative equals 0, right? So we want to take the derivative, but the problem is we have two variables. I don't want to derive two variables. I want one variable.
31, 75 minus x.
Yeah. So I'm going to sub out one of these using our other formula. That's why we have this formula. Okay. So pick a variable to solve for, x or y. I'm going to solve for y because that's what I did. All right. So I'm going to move the 70 over, or the 2x over, sorry, and divide by 2. And then I'm going to get 35 minus x is equal to y. Okay. Is everybody with me on that? All right. So now I'm going to sub that in for y in this equation. So that I will then generate area is equal to x times 35 minus x. Why is this a better, I don't want to say better formula, but for our circumstance, for what we want to do, why is this a better formula? It's the shape as a curve, and it's all x's. It's one variable. So I'm going to multiply that x in just to clean it up a bit. So there's our area formula with one variable. Now, I want to find the max of that formula. So what do? Take the derivative with respect to, not time, x. It's not a rate question, right? So we go dA dx is equal to 35 minus 2x. We good with that? Okay, if I want to find the max and min, I got to find the critical points, i.e. where the derivative equals 0, right? Because it has a horizontal tangent line. So you just set it equal to 0 and solve for, yeah. What is this? What units are we? Meters. Okay. We have to find out if that actually is the max. We have to prove it. So what we do to prove it, you have two choices. You can do the first derivative test. So that's the one where you go, okay, 17.5. You pick numbers on either side of it. So what would be the easiest number to pick on the left side?
17.
I would go with 0, but it doesn't really matter. All right. Any number that's less than 17.5. So if I put 0 into the first derivative, this is the first derivative. Do I get a positive or negative answer? Positive, right? Because the x will just go away. So I will say dA dt is positive, which means the function is going up. Then pick a number on the other side. You can pick any number you want. I'll pick 100. If I put 100 into the first derivative, I'm getting a negative number, which means we're going down. If you switch from increasing to decreasing, you are at a. Therefore, x is equal to 17.5 meters is a max. So we've shown that it is max. Now, you can also use second derivative tests, and I'll show you in these cases, sometimes it's easier. It depends on what you prefer. Or second derivative test. Derivative, I can't spell derivative. Test. So you have to find the second derivative. Remember when we did this before, I said finding the second derivative is pretty easy with its polynomials. What is the second derivative? Here's our first. What is it? It's negative 2. D squared A over dx squared is equal to negative 2. It's negative 2 everywhere. The second derivative is negative everywhere. What does that tell you? That it's concave down, right? And so at your critical point, if you're concave down, you must be a maximum, right? Therefore, it's a max at x is equal to 17.5. Okay, we have one last thing to do. We have to find the dimensions. So just plug it into your perimeter formula, essentially. Or, well, I would plug it into this one right here. Y is equal to 35 minus x. And you get 17.5, i.e., what shape is it? It's a square. Square with dimensions of 17.5 by 17.5. Boom. We're gonna do 3 examples today.
So,
yeah,
this will be divided 70 divided by 4. Is that what that is?
Hang on. Sorry, what?
70 divided by 4. So is the square always having
The square will be the max volume for
everything?
not well for a rectangle. Yeah, if you're looking for maximum volume, it'll be a square. All right. Okay. Flip the page. Let's do the one on the next page. So we're going to increase the level here. All right. Create the largest open box, so no top, that has a square base and a surface area of 108 centimeters squared. Okay. So I draw a picture. right. All right. So it's a square base. What does that mean that the dimensions of the base are? Something's a square. Yeah, but the sides are the same, right? So for a square base, that means that I'm just going to use x again. That and that have to be the same, right? Now, the height doesn't. That could be whatever. That's a different variable, all right? Because we don't say anything. We don't say it's a cube. So I'm just going to call it h for height. You can call it y if you wanted, but I'm just going to use h. We're looking for the largest box, okay? So we're basically talking about volume here. What's the formula for volume? X squared h. Okay, that's what we're trying to maximize is the volume formula. What's the problem with the way it's written right now? An h and an x, two variables. Okay, so do we have another formula? Or do we have other information? They tell us the surface area, right? So surface area, which is 108. Now, how do you find the surface area? Add all the area of all the sides together.
Yeah.
So, what is the area of that side? How many of those sides are there?
4.
There's 4 of them.
Oh,
There's-
square base.
It's a square base. So there's this side and the back, which is what you got. But remember, because it's a square base, what's the area of this side here? X times h, right? So there's 1, 2, 1 at the back, and 1 over there. 4 sides. Does that make sense?
Well, the way it's drawn, it looks like a rectangle prison.
I do a rectangle.
4xh. Does that make sense? Sorry? Oh, we're not done yet. We have to do it. So this is the sides. Okay? But there's also a bottom side, right? What's the area of the bottom?
X squared.
X squared, because it's this times this, right? No, it's not. Like if you drew it, if I drew it three-dimensionally like this, what's the area of that button there? It's x times x. It's this times this.
Is it, like, it says it's an open box, so we calculate the top of it as well?
Nope, because there's no top.
Okay.
So it's going to be the area of the sides plus the area of the bottom, which is x squared. This is the bottom. So this, let me just rewrite this. We have 108 is equal to 4xh plus x squared. There's our second formula. That's the area of all the sides of all, whoops, of this side plus this side plus the side there plus the side on that side. Okay, that's the 4xh. Does that make sense to everybody?
Yeah. I still don't know why it looks like a prison. Like a rectangle prison. It's freaking me out.
I just didn't draw the bottom as a proper square. Okay. So we got 108 is equal to 4xh plus x squared. What am I going to do with this formula right here? Solve for h. You could solve for x, but it's going to be a little trickier because there's multiple x's. So we're going to solve for h because I'm going to want to plug it into there. So 108 minus x squared divided by 4x is equal to h. I'm going to clean that up because I don't like it. Single denominator. So that's going to go to both terms. I'll write it out, but in the future I won't. So it's going to look like this. Which then turns into 108 divided by 4 is 27 over x minus 1 over 4 or x over 4. I'll just write x over 4. Does that make sense?
How do we get rid of all the extras?
Hmm?
Oh, it's
108 divided by 4 is 27. The x is still there. X squared over x is just x.
Oh.
Okay. That goes into that. So we get v is equal to x squared 27 over x minus x over 4. Now we only have one variable, right? X, that is volume. And we're trying to maximize the volume. That's the thing we want to derive. You always want what you're going to derive having one variable. But we can clean this up before we take the derivative because I don't want to use product rule on that. So I'm going to multiply the x squared in. That's going to give me 27x minus x cubed over 4. Is everybody good? All right. Now we take the derivative with respect to x. Now the calculus. It's always going to be with respect to x because I'm saying, how is the volume changing as x changes, right? So I get 27 minus 3x squared over 4. We good with that?
Yeah.
Yeah? Okay, what do we do now? Set it equal to 0 because you have to find the critical numbers. And then solve for x. So get x is equal to plus minus 6. Yeah? Does negative 6 make any sense here? No, because we're doing measurements, right? So we're just going to ignore the negative 6. Therefore, we're using x is equal to 6. Okay. All right, we have to prove it's a max. I'm going to do first and second derivative. You only have to do one, so it's your choice. If we do first derivative, that's when you're testing either side into the first derivative. I'll just say v primed. Because this is a measurement, right? X is a measurement, so it doesn't make any sense to... So v prime, pick a number smaller than 6. 0 is the easiest, or 1, or it doesn't matter. If I put 0 into here, what do I get? 27. It's positive, right? So the graph is going up. If you pick a number bigger than 6, pick 1,000. If I put 1,000 into there, I'm going to get... Let's go down. So we know it's a max. You don't have to do second derivative, but I'll do it just because. You have to find the second derivative. What is the second derivative? I'll say negative 6x over 4, or negative 3 halves x. What you want to test is you want to do the second derivative at 6, right? Because that's your critical point. So if you put 6 into the second derivative, are you getting a positive or a negative number? You're getting a negative number. Therefore, it's concave down at your critical point, which means you have a max. So it just, you do not have to do both tests. You only have to do one of the tests. I don't care which one you do. But this is just illustrating taking the second derivative for polynomials is straightforward. So that's why second derivative sometimes is faster, especially if you're doing a whole bunch of points. All right, so negative, concave down. So we know it's a max. We have to find the dimensions. Just use formula for h. This one. H is equal to 27 over x minus x over 4. What was it? 27 over x minus x over 4. Is that it? 27 over 6 minus 6 over 4. I don't know. What is that? I think it's 3. What is it? Is it 3? 3 centimeters. Therefore, it's 6 by 6 by 3. So what this is saying is if you have a limited amount of material, so you're building a box, okay? And you are given 108 centimeters worth of material. And they say you have to make an open box with the largest open box you can. The dimensions you want to build are 6 by 6 by 3. And that will give you the max volume. If you change those dimensions, every volume will be smaller than that. That makes sense? And if you look at the graph, if you actually, here, let's just do, I can put this into Desmos. What is the formula? 27x minus x cubed over 4. If we go to Desmos, (27x minus x cubed over 4). Is that it? Oh. There we go. When x is 6, this is the area here, or volume. When x is 6, that gives you the maximum volume of 108. Okay? And if you go past that, it starts to go down. All right? And if you're on the other side of it, it's down as well.
What if you go to like our side? It's
Well, these are negative values,
yeah,
so that doesn't make any sense. Okay? All right. One more question, then I'm going to give you a couple to do on your own. All right, a cost question. So we're doing a rectangular box again with a square base. So all that stuff's going to be the same. So we can draw a shape. I will try to draw a proper square base so that we don't have critiques here. Oh, maybe I can just do this. It doesn't have cubes. Think I can do this? That look the same? Good enough?
That's nice. That's good.
That meets your expectations? Okay, so square base. All right. Where is it? Where does it say square base? Square base. So I'm going to call it x. X, the height we don't know. This time we have a cost limitation. All right. We're only given $144. They tell us the material for the top, and we have a top as well. The material for the top and the four sides costs $1 per square meter. And the material for the bottom, I guess because it has to be stronger, costs $2 per square meter. What are the dimensions of the box with the largest volume that you can make for $144? So we know it's going to be volume. So volume is going to be x squared h, just like the one we just did. Now, let's look at surface area. Because surface area has units of squares, right? So we need to figure out the surface area of this. So, surface area. Now we got to go through this step by step because there's different costs associated with it. But we know that all the sides, four sides, have the same cost. So what is the area of all four sides? What's the area of one side? Like this side right here. What's that area? X times h, right? And there's four of those sides. Does everybody agree with that?
Yeah.
So we can go. So let me go. What do I want to say here? 4xh. This is the area of the sides. I'm just writing its title below. Plus the area of the top. Now the top has a different cost than the bottom, so I don't want to lump it together. What's the area of the top?
X squared.
X squared. Does everybody see that? Like this bit right there. That's going to be x squared, right? The green bit? So that's going to be x squared. So this is the area of the top. Plus, now the area of the bottom has a different cost, but what is the area of the bottom? It's going to be x squared as well. Don't add those together. Area of the bottom. Okay, that gives us our surface area, but that's not what we're restricted by. We're restricted by the cost of $144. So if I want to generate a cost equation for this, they're charging us $1 per square meter for the sides and the top. If we have this much surface area for the top and the sides, what do I multiply these by? $1, right?
Yeah.
Does that make sense?
Yeah.
So this is going to be $1 for xh plus $1 x squared plus how much does the bottom cost? $2. So that's $2 times x squared. So if you just clean this up, you get a cost equation. And we know the total cost has to be $144.
Did you add the X squared together?
Now you can add them together. We didn't want to do it before because there's different costs associated with it. So now I'm going to go 144 is equal to 4xh plus 3x squared. Okay, what do we want to do? Solve for h. There we go. We can clean that up and get 144 over 4, 36 over x minus 3 over 4x. Okay, where does that go? Into the volume equation. Right there. So I get v is equal to x squared now we're going to clean it up. So I'm going to multiply the x squared in. So I'm going to get 36x minus 3 over 4x cubed. And now you can derive it. Now you can do the calculus. Oh, did I write t? Sorry. dv dx. And then everything, it's once you've done that, the hardest part is setting up the equation. And then once you've done that, it's just derive, set equal to 0, solve the dimensions. Go. Yep, x squared. Thank you. I'll let you do the proof. Is that it? 4 by 4 by 6? All right. So, let's see if we can come up with some rules here. All right. You can do it on the back of your sheet or wherever you have space. So what are we trying to do? What are the steps? What should you do first here when you're solving these types of questions? I would draw a picture. Don't have to, but it usually helps. Draw a picture. Then what? Find an equation. So you want to find an equation for the variable you're trying to maximize or minimize, okay? So equation for variable you are max minning. That's not grammatically correct, but I don't care. Okay? You're going to max min. So volume, surface area, whatever. Then you want to have an equation for the restriction. So they restrict your cost, or they restrict the amount of material, or the perimeter, things like that. So I'll call that the restrictive equation. That's, yeah, where they give you a certain amount of material or a certain amount of money or whatever they're trying to do. Okay, once you have those two equations, what do you do? Yeah, you solve for one of the variables and sub into the other. Sub into, I'll say number 2, which is this one right here, into the equation for that variable. Then it's just, then the calculus starts, right? So then it's derive, take the derivative, find your crits.
What does that say? You are maximum.
Yeah,
Oh,
you are maximizing or minimizing.
okay.
I just shortened everything to be, all the English teachers would be turning over right now, but we're not in English class. So take the derivative, find your crits, and the final thing is to test to prove it's a max min, and I guess then find dimensions. Yeah. Number 4 says solve for variables and sub into equation 2, into this equation right there. Yeah. Yeah. All right. How do we feel? Okay. These can get nasty depending on what you're doing. We're starting out with some straightforward ones. So page 220, numbers 9, 11, and 19. Please.